Study on thin film oxide and the related functional heterostructure. So I start by some basics on SPM, and then among the hundreds of modes that have been developed from SPM, I will focus on 3 of them, namely the scanning, the other one, scanning resistance AFM, piezo response AFM, and scanning NV magnetometry. For each of them, I will explain you the principle, how it works. I will show you examples obtained on thin oxide films. And I will also give you practical tricks and advice to avoid the main pitfalls to perform these measurements properly. So what is SPM? So the concept of SPM is exactly the same thing that how blind people can reproduce a surface in their brain just by scanning a surface with their finger. They do that and they have the image in their brain. We want exactly to do the same thing. Except we want to do that at the nanometric resolution. So how to obtain this resolution? There is several requirements for that. The first of one is, of course, you have to be able to position your finger with a nanometer precision relatively to the surface in the 3 dimension. And this is going to be the job of piezoelectric materials and ceramics, in fact. Then you want to have a probe sample interaction limited in space. So this is related to the tip geometry. You want a small finger, as small as possible. And also you prefer short range interaction. Okay, so you all know what is a piezoelectric. So you apply an electric field, you obtain deformation. And if you take the most popular piezoelectrics used for this kind of application, the piezoelectric coefficient is about 100 picometer per volt. And so if you apply 100 volt, you get 10 nanometer distortion, 1 millivolt, 0.1 picometer. It's pretty cool, but if you want to scan over microns, it's not enough, and you don't want to apply 10,000 volts, you will burn it. So to do so, you just have to shape your piezoelectric as a thin sheet, and for a small, because you have to maintain constant volume, for a small distortion in the transverse orientation, you can have quite a large motion in the longitudinal one. So we have a material, how to do a piezo scanner, a real one. The easiest way is to shape your piezoelectric in the form of a hollow tube. And then you put your sample on the top. You will understand why later on. So, and on this piezo material hollow tube, you deposit 4 pairs of electrons, X and X bar, Y and Y bar. Now, maybe here. So, if you apply a positive voltage here and a negative voltage here, the material is going to expand on this side, to shrink on this side, and as you can see here, you scan on the Y direction. The same for the X and the Y. And now, if you apply the same voltage on the 4 electrodes, then the whole tube is going to expand or shrink, and you have your Z motion. And finally, one position in space is going to be 3 voltages. A surface in space is a file of voltages. It's a matrix. And with the piezoelectric relationship, you can transform this matrix in a surface. Okay, the typical XY scan range of a modern AFM is about 100 micron, and the Z range is about 10 micron. Now the finger, the probe. You want the probe as small as possible, so that's why they are fabricated with microfabrication techniques. So this is a scanning electron microscope of such a probe, an AFM probe. And for different probes, as you can see here, you can have very different radius, ranging from 2 nanometers to hundreds of nanometers, sometimes micrometers, depending on what you want to do, but it is another story. And of course, the shape of your probe is going to rule your lateral resolution. So here we are. This is the general principle of the SPM. you need a piezo. I split them, but in some systems they are splitted. So I have the piezo scanner here, XY, the piezo Z, holding the probe. And then the probe is going to interact with your sample. And then you want to measure this interaction, and this measurement is going to feed in a feedback loop that is going to modify the piezo Z distortion to maintain this interaction constant. So in SPM, the map you obtain of a surface is defined by Z, X, Y, of course, and Z as an interaction always constant. So the simplest SPM is the scanning tunneling microscopy. In this case, the interaction is a tunneling current flowing through the tip to the sample. If you polarize it, and then you measure this current, feedback loop, and you will distort this Z piezo to maintain this current constant. So this invention was extraordinary since it was the first time it was possible to see the atom on the surface. A revolution, yes, but this mode is limited to conductive materials. There is a mixing of the topography of this, in fact, what you think is the topography, with the local dose, as you can see here. If there is, for any reason, more electron in a place, for example, because you have a doping atom, then there is more current, and for the system, it appears like a bump. And also, the most important limitation with conducting material is you have to use ultra-high vacuum, because if you can see atom on the surface, of course, you don't want to have any foreign atoms on your surface. So that's why rapidly people thought maybe we could use something else than the tunneling current. And this is the idea of the atomic force microscopy. So if you look at the interaction between the atom of your probe and the atom of the surface, it looks like this. Far away, there is no force, of course. And as you come closer, you have first an attractive van der Waals forces. And then if you come even closer, you start to have a very strong repulsive forces, which are exactly the same that makes your finger not to pass through the table. Huh? It's just this. Okay, but how can we measure those forces? This is the concept of the cantilever, and that's why I have this ruler. A cantilever is a bendable structure holding the tip. It's like this ruler. It's a spring with a stiffness K. It's all based on microfabrication technologies. And here you have an image. This is the tweezers. This is your ship. And at the very end here, you find this, a ruler with a small tip below it. And the K can be modified essentially by changing the geometry of these things, or also you can change the material. So it ranges from fraction of Newton per meter to hundreds Newton per meter, depending on what we want to do with this. Okay, so if we can measure, okay, first, the concept is very simple. When you're far away, no force, the cantilever is flat. When you come closer, attraction forces start to play in the game, and it bends down. And if you push stronger, it bends up. So if you are able to measure this distortion with the Hooke's law and the stiffness, you can measure directly the force that is acting on the tip, not on the cantilever, on the tip. How to measure the cantilever deformation? In the seminal paper written by the inventors of the STM, they use an STM tip on the top of the cantilever. So it's not very convenient, taking into account our goals today. So we invent something much, much more simpler. You can see the idea here. So there is a laser diode, and the laser is reflected by the back side of the cantilever, and is reflected on these two photodetectors. And you see, when the cantilever is distorted, the laser is going to move between 1 and 2. And if you make the difference of those two voltages here, you obtain something, a voltage that is proportional to the force, that is proportional to the deformation of the cantilever, and is proportional to the force that is acting on the tip. So it's very simple. With this system, the atomic interaction measurement is resumed to a voltage. Okay, there is a geometrical amplification. So you can readily obtain vertical resolution, please, below 0.01 nanometer. Okay, first advice, please, focus the laser at the very end of the cantilever. Sometimes I can find on my systems the laser tuned here close to the point, and clearly you don't need more explanation to understand it's not very clever to do that. So here we are. This is an atomic force microscope. We have the general scheme here, and we are using atomic interaction between the tip and the sample. And what is measuring this? This is this block, cantilever plus laser plus photodetector. And of course, the surface you will obtain with such a system is a surface defined by the deflection remaining constant. How it looks? So this is one of the most popular, very old system of the 90s, which is called the nanoscope from Digital Instrument. So you can see here you have the piezo tube and the optical head. And this optical head contains the laser that comes from the top. The cantilever is here. The laser is reflected on the mirror and go to the photodiodes here. You have two screws to focus the laser on the cantilever and one screw to properly tune the position of your photodiode on the laser. Okay, a small movie. I like movie. Working movie. So this is a real scanning electron microscopy observation of a working AFM. Note how big is this stuff. The probe and the cantilever compare what you want to measure. So the tip is engaged, and it starts, the small fingers start to scan the surface, and the surface is reconstructed each line by each line, slowly. Okay, I like it. Okay, we can, at this stage, you can make some IFMs directly. You don't really need to know exactly the force you are using, but sometimes you need to know the force that is related to your deflection. So to know that, first of all, you have to know the relation between deflection in volts and the actual cantilever deformation. To do so, you make what we call force curve. It's very simple in principle. There is no scan X, Y, and you just extend and retract the Z piezo. And this is... Ça marche comme ça? No, ça marche pas comme ça. And this is what you obtain. Far away. Aha. Far away, there is no deflection, no force. Then when you come closer, you can see that tip jump to the surface because of the attractive forces, and then you push, you push, and the laser is deflected. And this is what you can see here with a linear slope. If you reverse this slope, you obtain what we call the sensitivity of your system, which gives you how many nanometers you distort your cantilever for each volt of deflection you measure on the photodiode. Remember that this is purely geometric. It's related to your IFM geometry and the length of your cantilever. Whatever the stiffness, whatever the width, whatever the material, it's just geometry. So once you have measured that for one kind of IFM probe on your system, normally you don't need to measure it again. But you have the distortion, now you need the stiffness, of course. And just to simply relate the force to the distortion here. So, two ways. Either you believe the manufacturer's datasheet, but as you can see here, there is a large dispersion. It's related to the way this thing is fabricated. So the thickness is very difficult to control.
Can I ask a question?
Yeah?
I never understood why we let the laser beam diverge in this geometry, and there isn't, for example, a small lens that would converge the laser beam on a small spot.
Yes, but you are talking about something very recent, which is high-speed IFM, and for this you need very small cantilever to increase the resonance frequency. And that's why you need a lens to focus. Because when you have a laser that is 10 micron width, it's not important when your cantilever is 50 by 100 micron. But when your cantilever is 1 pi by 5, you need to focus it very precisely. So you see, if you want to be a little more precise, in modern AFM now, there is a method that is rely on the thermal oscillation. You don't excite your cantilever, your oscillator, but because you are in a thermal bath, it oscillates. And if you measure this oscillation and you apply a simple model, you can obtain quite precisely the stiffness of your cantilever. So here we are. You have the sensitivity, you have the stiffness, you know the force. Let's talk about spatial resolution, which is very important. So the vertical resolution is always very good. It is related to your ability to measure the smallest cantilever deformation. Essentially, sorry. For the lateral resolution is a little bit more complicated because it's going to depend on the two things I told you before, the tip geometry and the type of interaction. Okay, if you have a too large radius and short range interaction, bad resolution. Infinitely sharp tip, long range interaction, bad resolution. And of course, you would like to have an infinitely sharp tip and short range interaction. Okay, there is two main modes to measure the topography of your surface. The first one, the simplest one, the first one that was invented is so-called the contact mode or static mode. In this mode, you simply, you simply drag your tip on the surface. So you come here, you apply a given force, and you scan. As you can hear, you're gonna have problems. Huh? So as you see here, the system drags the tip and the cantilever deflection is maintained constant thanks to the Z, piezo, and the feedback loop. We are working in this regime of high repulsive forces. So it's very simple. It has several advantages. One of them, but it's the same for other modes. As you use quite high forces, any surface position is going to be swept away, and you can work in ambient condition, in liquid, there is no real limitation. The contact is permanent. So this kind of scan is compatible with measurement of electrical current, temperature properties, some mechanical properties, like tribology. And the drawbacks. So the force, the high force I said, but can seem pretty small, but the surface of your problem, the surface is very small. So you are in the gigapascal range. And with this kind of pressure, you can distort your sample or you can distract your sample. Also, because you're dragging the probe on the surface, there is high friction forces. So you have tip wearing on breaking, and the tip sharpness is limited not by fabrication process, but by the mode itself. You can bring the sharpest probe you want in this mode. After one line, your tip is broken. Okay, that's why the dynamic mode was invented. In this situation, you don't just drag your tip on the sample. You are going to use the properties of the harmonic oscillator the cantilever is. So it's an harmonic oscillator, so it has a mechanical resonance. You're going to do that. And the cantilever oscillation is going to be modified by the force acting on the tip. This is a general principle. So here, the feedback parameter is not deflection anymore, but it's an oscillation parameter, either the frequency or either the amplitude of the oscillation. Advantages. First of all, at the resonance, the harmonic oscillator is very sensitive to perturbation. Also, measuring frequencies or using lock-in amplifier gives you access to very small signal. So this means small signal, lower forces. And the last but not the least, there is no more friction forces. So you can have very sharp probes. So what happens to an oscillator when it feels a force? So you know this very simple equation. This is a harmonic oscillator. If you add a force now, you can solve this equation very easily if you can expand the force at the first order. So if you do that, that means that the force experienced by the probe along the oscillation of the cantilever do not vary too much. Okay? It's the case most of the time. And so here, there is only this that remains a variable. All those are just numbers. And finally, you find that the resonance frequency is shifted. When the tip feel a force, the cantilever resonance frequency is shifted. Okay, so if the force is attractive, the resonance frequency is reduced. If the force is repulsive, the resonance frequency is increased. Simple. So now, let's assume that we are working in a forced oscillation scheme. Why? To use lock-in amplifier. So you won't track the resonance frequency itself, but you are going to measure the amplitude at a given frequency. So imagine you choose an excitation frequency, which is exactly the resonance frequency. If the force is attractive, at this frequency, the amplitude decreases. If the force is repulsive, at this excitation frequency, the amplitude is decreased. You don't know what to do. Is it a bump or is it a hole? The feedback loop needs to know what to do when the feedback parameters increase or decrease. It cannot be bijective this way. So that's why you have to tune your excitation frequency a little bit off from the resonance frequency. Here you see, if the force is attractive, the amplitude increases. If the force is repulsive, the amplitude decreases. So your feedback loop knows what to do. If the amplitude decreases, it means that it's a bump. It means that the repulsive force is higher, so Z is increased until this amplitude come back to the set point amplitude. Okay, so amplitude modulated mode. This is the name. Yes?
In the slide where you were showing the movie about the displacement and deflection, the force deflection,
Yeah?
it looked like the attractive part of the interaction was unstable, as in like the second you get too close, the stick.
Yes, there is a jump. But it depends on the stiffness, of course. If the stiffness is high enough, you won't get a bump. You will get something much smoother.
Then is it possible to then stabilize a situation in which the tip is not actually in contact with the surface, but is just hovering above?
Yeah. Yeah, it is. Yes, it is possible. This is used in what is called non-contact AFM mode, something really advanced to obtain the atomic resolution with an AFM. We can discuss that afterward if you want. But in a regular AFM, commercial AFM, if you use the attractive mode, in fact, it's extremely unstable because it's not, as you see, there is two attractive. You should have stayed to the beach. So you see that there is two attractive forces for two different distance. I'm left-handed, that's why. See what I mean? So it's unstable. And there is a way to avoid this, but with very small oscillation amplitude. We can discuss that later on if you want, but it's another word, in fact. So this is so-called amplitude modulated mode, but everybody call it tapping mode. You understand why. And so you take your regular AFM we had at the beginning of the lecture, and we have the cantilever, the laser, blah, blah, blah. And then I will add here on the cantilever a small piezo stack that is fed by an AC voltage. So this guy is going to oscillate. By mechanical coupling, the cantilever is going to oscillate. And then, thanks to the photodiode, this oscillation is in the signal of the photodiode. And then you just have to add a lock-in to take the signal, add a lock-in which is locked on the excitation frequency. And then you obtain the amplitude, which is the signal that you're going to use in the feedback loop. And here, the surface is defined by amplitude equal constant. This is how it works. Far from the... Ah. Il y a un truc là. Okay. Ah. Please. Sorry, guys. Okay. Far away, you have the free amplitude. While once engaged, the amplitude set point is smaller, of course, because you want to interact with that. And this is always the same story, huh? Okay. Advantages. First of all, you can measure smaller signal, so you can measure lower forces. So you can work on soft material. This mode is typically used for everything, but especially for life science, polymer stuff, and all the soft material has to be observed with this mode. As I told you, there is no more friction forces. So you can use much sharper tip and you have a much better resolution. That's why most of people use this mode even to observe hard materials, huh? Better resolution. The drawback, so it's a little bit slower than the contact mode because of the dynamic of the oscillator. And there is no permanent contact. So it's going to be impossible to measure current, temperature, or things like that. Yeah. Where are you? Okay, you. No, not you.
No.
Come on.
No,
Navette or question?
question.
Okay. I remember that.
So you mentioned that we have a piezo at the end of the cantilever, the tip that we apply the AC voltage, right?
Yeah.
And the frequency of this AC voltage should be lower than the frequency of the
Resonance frequency.
resonance frequency.
Yeah.
But is it resonance frequency or the free amplitude?
No, the excitation frequency has to be smaller than the resonance frequency. But if this is your free amplitude, of course the set point means the amplitude used to probe the surface is smaller because you want to interact. Okay? So this is one of the first examples to compare what you can do on these things, epitaxial silicon with contact mode and tapping mode. Okay, no comment. The probe, your finger. Okay, in AFM, all what is seen by the tip. So your tip is probably the most important object in your system. And there is a lot of artifact that can come from this. So first, let's characterize a probe. So an AFM probe is characterized essentially by its radius and by the cone angle here. Tip radius, related artifact. So if this is your sample here, you want to make an image of this guy, and this is your probe. If you scan your probe, this is the image you will get. And in fact, if the radius of the object on the sample you want to image is much smaller than the tip won't image the surface. The surface is going to image your tip. Another one, very simple also, if you want to measure a step, if the step is too steep, in fact, you will measure the angle of the probe itself. But this one is very easy to detect and to correct, not to correct, to detect, because the tip geometry is very well known. Of course, you have to think in this way, but in 3 dimensions. For example, you can transform this little dot in a nice little square if you are using two big pyramidal tips. And some example. Okay, when you see that on your sample, okay, what's going on? probable damage tip, or maybe if you have something growing with a threefold symmetry, could be your sample. Rotate the sample. If the shape remains the same, it means that the sample is imaging your probe. And then you have this mantra, change the tip. You change the tip a lot in IFM. Another example, this is probably a double tip. Quite easy because you can rotate also and this won't change. But this is less clear. So if you have any doubt, change the tip. This kind of tip can cost 15 euro. Huh? Don't waste half a day or weeks by measuring with a broken tip. Okay, so now at this stage we can make the topography of any surface in a static mode or in a dynamic mode. But of course we would like to do something more exciting. And there are lots. I've read somewhere, I was not able to find back the reference, that something like 250 modes were developed from the initial SPM ID. So you can measure, in surface science, can measure electrostatic properties called electric force microscopy, Kelvin probe microscopy, MFM for magnetism, scanning resistance IFM for conduction properties, piezo force, thermal, you can measure thermal conductivity, temperature, blah, 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 blah. You can even measure optical properties with a resolution well below the diffraction limit. You can use quantum sensors. This is scanning anti-microscopy. And I won't talk about all this. So today, of course, you can have the atomic and molecular resolution. You can stretch on molecules, make lithography, and so on. So before coming to the three advanced modes I wanted to describe in detail, let's see a mode that allows to measure long-range forces. So how is it possible to measure long-range forces? This is the concept of two-pass mode or lift mode. So in the first pass, you use tapping mode, and you are going to use a set point strong enough to make the short-range repulsive forces to dominate all other forces. It's quite easy because other forces usually are quite small. And then, thanks to this, thanks to this, you can determine the atomic topography. Then, in a second pass, you remove your tip from the surface and you will follow the topography you've just recorded, but at a constant height. And because of this constant height, you know that van der Waals forces are constant. So you will only measure long-range forces coming from either magnetic field or either electric field. This way. Clear? Easy, huh? Not too complicated. Okay, so if you cover your tip with a conductive material like platinum, you can measure electrostatic forces. So this is AFM and KPFM. You can measure trap charge, surface potential, and even voltage drop in a working circuit. If you coat your probe with a magnetic coating, you will measure magnetic forces, of course also electrical forces, but you can make the difference. And then, as you can see here, you can measure topography and some funny domains in the disk. Okay, so let's start with other advanced mode. Let's start with the scanning resistance IFM, the simplest one. So in this mode, you use an IFM in contact mode, and you polarize the probe relative to your sample with a conductive tip, and then you measure the current flowing through the tip. Easy. So you can do that simultaneously. There is no link between the feedback loop and so on. So you obtain a simultaneous mapping of topography and local conductivity at the nanometer scale. What do you want to do so for your current amplifier? Of course, you want everything at the same time. You want something with high bandwidth to be quite rapid and measure image in a reasonable time. You want high gain to measure the lowest current possible. But you want high dynamics too. And most of the time, you have to make a choice here. The probes, the finger, always the probe. Okay, these are two typical conductive probes that are used in this mode. This is a platinum-coated tip. As you can see, the radius is pretty small. It is directly related to the thickness of the layer you deposit on your probe. So you have a small radius, but it's really experience fast wear out if you don't pay attention. And the serial resistance is small, so that means you can measure quite conductive samples. On the other side, there is the polycrystalline boron-doped diamond-coated tip. Okay, quite ugly, with a large radius, but these are so strong. So, if you can use this, I advise you to use this one. And the serial resistance is a little bit higher, about 5 to 10 kilo ohms. And there is many other probes, but most of the time you switch from this one to this one or the contrary. The real life of a probe. So this is a scanning electron microscope image of a platinum-coated probe before using it, after using it, after another after. And okay, you are going to realize that this is a citation of Mr. Stéphane Fusil, a co-organizer. You have to be ready to kill a lot of probes to work. But most importantly, you have to be able to characterize your probe before experiment, during experiment, and after experiment, just to know if your measurements are true or not. So to do so, to characterize a conductive probe, we are going to use what you know now, a force curve on a conductive film like gold, for example. This is the force curve. No contact, jump to contact, you push on the surface. And this is the current you can record at the same time. Saturation, when you touch surface, the resistance decreases a lot, and you reach the minimum resistance here. If you make an IV, you can see it's nicely linear. And this is the requirement for good probes, a simultaneous contact, a low resistance, and a linear IV. If you use a boron-doped diamond tip now, coated diamond tip, you can see that the resistance starts to decrease at the first contact, but you need to use quite a high force to reach the minimum resistance here, which is about 5 kilo ohms. The IV remain linear, but you need a slightly higher force. This is a brand new one. Huh? So this is your reference. When you measure, then you are able to say, have you got a problem? And here, clearly, you have a problem. You can see that the minimum resistance is obtained after a huge force above 10 micronewton. The minimum resistance is extremely high, and IV is not linear anymore. Okay, let's make our first scanning resistance IFM experiment on a gold layer. If you apply a low force, okay, here it's important in this part of the talk, pink is insulating, red is highly conductive, and then between, okay, it's a logarithm scale. Huh? So if you don't apply high enough force, gold is insulating. You increase the force, and at the end, at 1 micronewton, you obtain the series resistance of your probe of 10 to the 4th ohm. Yeah?
So this force that you are indicating here, does it include the capacitive force that you have between the tip and the...
Absolutely not. It's just the force applied by your cantilever.
Right, so how do you account for...
I don't. This kind of cantilever has a stiffness of 40 Newton per meter. So I think that the capacitive forces in this case are definitely negligible. So, thanks. Gold is conductive. Your first result in scanning resistance microscopy. So, what's going on there? If you, at the end of your measurement, if you increase the scan range a lot, at least to have a good vision on what you have done before, and you reduce the force or even switch to the tapping mode, yes.
About this measurement first line. So you apply 2 volts
Yeah.
with a resistance of 10 to the power 4 ohm.
Yeah,
This is 0.1 microamp.
probably.
Yeah. Do you really
Yeah.
drive force of a milliamp?
Yeah, this is the limit. Huh? Typically, for a diamond one, I don't know, but for a platinum one, 2 milliamps, you'll start to burn everything. Of course, you're right. You don't want to apply, but you can reduce the voltage if you want. But in this case, this is my classical procedure to characterize the probe. And believe me, I won't destroy my probe by characterizing them before experiment. Believe me. And so then here you can see that what you have done here, to reach the gold, you dig something like 1 nanometer in something. And this something is adsorbate on the surface. And in fact, in this mode, significant forces has to be applied to obtain a good electrical contact, stable electrical contact, at least in the ambient atmosphere. But you're working on oxide, so everything is going to be okay. For other kind of material, it is definitely a problem, and there is solutions. Okay, so a full slide of ideas, yeah, what you have to do to make proper experiment with this mode. Characterize your tip with force curve. Check IVs on your samples. Sometimes, for some samples, depending on the probe you use, you can have Schottky, you can have things between your probe and your sample. So, and you want to make this as small as possible because you're not interested in the contact of your probe with the sample, but with your sample. Check the topography after your conduction imaging, as I showed you. And if during experiment you don't understand what's going on, change the tip again. If it remains the same, then start to think a little bit about your experiment, what's going on. Okay, few examples of what can be done in oxide with scanning resistance AFM. A very simple example. So this is a bismuth ferrite. You will see this guy a lot, even in my talk. Sorry. Huh? This is an international school on BFO. So this is a FM topography. You're starting a new materials. You try to grow it, and you put it in your IFM. A lot of bumps, probably parasitic phases. And when you use a scanning resistant microscope, you can see that those things are conducting and short the layer of BFO to the substrate. So don't try to make any capacitor to make P loop measurement on this guy. It's useless. So it's a good in for you to progress in your optimization. Here you can see an image, a scanning resistance image of BFO on an electrode, but only 5 nanometers. You see you have nice atomic steps, and the resistance is homogeneous in the about 10 to the 9th, but we don't really care about the actual value. And more importantly, if you change the thickness of the BFO, here, in this case, you can see that you obtain a nice exponential dependence, showing that you have effectively what, excuse me, you have a transport of electron by tunneling. Yes.
Question. If now we were showing a scanning current, does it make sense to call it resistance? You just plot a constant bias.
Yes, you're right. Let's say it's exactly just a convention. You're looking for, this is what you're looking for. Of course, if the IVs are highly nonlinear, you won't get your exponential dependence. You're right. Yes, it is necessary. You can afford it.
When you do measurements that you test, you scratch the surface and see if you measure the same kind of
what I meant is you have to do it, but in fact you don't have to scratch. You have to apply high enough force. In some cases, for some materials, the kind of force you want to apply will be a problem, but for oxide, most of the time it's okay. That's what I meant. But there is something. Huh? Yes. Yes, it's kind of cooking. Huh? It's not real physics. This is another example. This material is a ferromagnetic insulator, and we wanted to grow thin films on an electrode to fabricate spin filters. Okay, so we had to characterize these very thin insulating materials, and it's usually not that easy. But here, if you use the scanning resistance microscope, okay, here you have the measurement on the bare electrode. And then we had 5 nanometers of NFO, but in a pure argon atmosphere in the sputtering chamber. And it was green, it remains green. Not very good sign. As soon as you had 10% of oxygen in your mixture, for exactly the same thickness, you increase by at least 2 orders of magnitude the resistance that is measured. And in fact, as you can see here, with no oxygen in the mixture, you have totally flat dependence of the resistance with the thickness, whereas, again, you can find the exponential, the expected dependence, to exponential dependence, showing that you are working in the tunneling regime. So it's very convenient because you don't have to go to the end of the fabrication of the complex microfabrication of tunnel junction to have an opinion on what you have done. Another example, this is a metal insulator transition on nickelate, and of course, you want to know what's going on there. So if you're lucky, and if you have a cryogenic AFM, you can try to observe what's going on at this transition. And in this paper, you can find that at low temperature, resistance is homogeneous with a high value. And then as long as you increase the temperature, there is some highland of low resistance that appear. And finally, they coalesce together at this temperature here. And here at high temperature, you have only remaining the conductive phase. And this one is my favorite. You all know, I assume, that you can create a 2D electron gas at the interface between insulator. But at this moment, see nature, huh? So it was not that obvious. So those guys published this paper saying, hey, wonderful, we made a 2-dimensional gas here with a high mobility at low temperature and so on. And anyway, it was not that clear, and there is a lot of debate and arguing and so on about is it a real carrier confined on the interface, because bulk STO, once loaded with oxygen vacancy, can behave the same. And if confined, the question was, what is the thickness of this gas? So to answer this question, we have developed a cross-section preparation to access the interface with the FM probe. And this is what we got. So usually lanthanum aluminate is deposited at low oxygen pressure. And if you don't pay attention, this is the result at the end. Your LAO is pink, insulating. The interface is, of course, a little much more conductive. And then the whole substrate, till to the end, there, 500 microns away, is loaded with oxygen vacancies and is conductive. On the contrary, if after exactly the same deposition process, you add an oxygenation step, so you remove the oxygen vacancies from the STO, it becomes pink, insulator, but it remains this nice high conduction line here, and then you can answer, yes, there is a gas of electron at the interface. And if you make a zoom and a cross-section, you can even give an upper limit which here is about 7 nanometer. Because of probe finite size effect, you cannot say it is 7 nanometer. It's at most it is 7 nanometer. Okay, second advanced mode. Yes.
Speaking about probe size, is it doable to deconvolute the tip side and try to understand what's the...
You are this kind of guy. No, I don't know if it's possible. I don't know if it's possible. Probably, but you have to know perfectly the I don't think, in fact.
Then most of the time when I find me to save it to PNG.
I don't think you can tell. I don't think. I haven't tried. I'm not this kind of guy. Okay, PFM. Well, some of you knows pretty well this mode. So ferroelectric material, you know. What is important is that all ferroelectrics are piezoelectric. And in fact, this is what we're measuring in this mode. So if you apply an electric field, you apply blah, blah, elastic deformation. So here, you are using contact mode FM, again, with a conductive tip. If you apply positive voltage on the down polarization, the material expands. Negative, it shrinks. And exactly the contrary if the polarization is reversed. Okay. This deformation, this static deformation of the material is extremely small. It's about, if you remember the figure I gave you before, it's between 10 and 100 picometers if you apply 1 volt. So it's possible, it was done, but it's complicated. So that's why people decided to switch to AC mode. So if you apply, instead of applying a voltage, you apply an AC voltage here. Once again, this guy is going to oscillate. This guy also, but the amplitude is supposed to be the same for the two oscillations, but they are supposed to be exactly in opposition of phase, because this guy goes up when this guy goes down, and the contrary. So this is how it works. Yes, huh? I told you it's a very nice talk for a post-lunch session. Okay, this is what's going on. Here you see the amplitude of oscillation is the same in all domains, but the phase lag is 180 degrees. So here we are. You take your AFM, classical one, and then so you can make a topography, relax. And then you apply a AC voltage between the probe and the electrodes below the ferroelectric. So oscillation, oscillation. But in this case, you just pick up the signal. This part remains the same. Those oscillations are small enough not to perturbate the measurement of the topography. But simultaneously, you pick up this signal, you feed it in a lock-in amplifier, which is locked with this oscillation, this excitation, and then simultaneously, you obtain topography, amplitude of oscillation, and phase of oscillation. And you can really see here that amplitude, okay, here you see up and down domains, black and white, and you see that amplitude are the same except it at the domain wall. So you obtain simultaneous imaging of the topography and ferroelectric domains. If you apply a DC voltage above the coercive field, you can write artificial domains. And if you stop scanning and you stay on the spot, you apply a small VAC AC voltage to measure the piezo response, and you sweep the VDC, you can reconstruct the cycle of local piezo response like this. And you can do that in many points, and you can make a mapping of the coercive field and so on. Okay, this is an example of what can be done. J'ai vu quelqu'un bouger. Okay, pristine domains. Here we wrote something. Here you see amplitude, phase, same amplitude, 180 degrees. Okay, so I told you, let's use AC voltage to excite the ferroelectric. Okay, which frequency? Take any one, and you will probably obtain this. This is a measurement on neobert lithium. And you can see that the amplitude of up and down domains are really different, and the phase contrast is really small. It's less than 20 degrees. You have to obtain 180 degrees. If you use an optimized frequency for the really same sample in the really same machine, you can see that the amplitude are the same for up and down domain, and the phase contrast is 180 degrees. What's going on there? In fact, it's a question of noise. Okay, but at a given frequency. I remember you that we are using lock-in techniques. So normally, all the parasitic noise, which is not at this frequency, is filtered out. So that means that we have probably, okay, this is a way to represent the Fresnel representation of P plus and P minus. Is it okay for you? So it's just an easier way to make addition with this guy. If you can do that by head, it's okay, but I can't. But I explain you. So here you have a noise, an additional noise to the polarization at the very same frequency, but with a phase. If you want to have the results of the addition of this noise to the different polarization, you make a vectorial addition, and this is the result. And you see that amplitude are dissymmetric, and the phase contrast is not 180 degrees anymore. Okay, but why this noise at this frequency? The main source of noise, one of the main sources of noise at the excitation frequency comes from the oscillation of the cantilever because of the capacitive coupling. You have to realize that it's small, it's extremely small, but what you want to measure is small too. You want to measure something which is 10 picometers in amplitude or 50 picometers in amplitude. So you can understand that with the surface that is a huge surface of the cantilever, the electrodes, you can obtain such an oscillation, such an amplitude of oscillation coming from that. So another advice for PFM, at least for out-of-plane PFM, prefer stiff cantilever. The stiffer, the lower the parasitic effect. And of course, please use an excitation frequency far from the cantilever resonance, which could amplify this unwanted effect. But it's not enough, because don't ask me why. I don't really know why each IFM at its own optimized frequency. It depends on your IFM also. So the best way is to take a reference sample. Most of the time, you can have something provided by the IFM manufacturers. And you try. Here on the same image, I've tried 3 different frequencies. And as you can see here, despite a low resolution, I'm not interested here in the resolution. I'm interested in the phase contrast. And obviously, this one is pretty good. Okay, reference sample, optimize your frequency. Once it's done, it's forever. Yeah.
When you choose the frequency, you have to choose where you have amplitude. If you are too far, there is no amplitude. So you are kind of forced to be like on the edge of the resonant curve.
No, I don't like resonance stuff. You don't control anything with that, because it's not. But you're talking about the resonance of the contact, yes, not of the cantilever itself. But for other people, it's important to make the difference. The problem is when you are using the resonance or close to the resonance, there is an additional effect you do not control that increase your amplitude. Okay? And you cannot control this effect. You don't know exactly what is the actual amplitude of oscillation of your material. And if you want to measure, for example, the D33 parameters, it's impossible. Furthermore, we have such a system in the lab, and we use it twice a year. Most of the time, we don't need that. What you need is a very good IFM. And up to now, to say the truth, the best one is a multimode from Bruker. very, very low noise. If you have a very, very low noise AFM, you don't need resonant stuff. Resonant stuff, to me, is something to overcome badly designed AFM. This is my opinion. Huh? But, for example, with a cipher from Asylum, most of the time you have to use the resonant stuff. But you can see the Virgin, you can see God with resonant, you can see 300 degrees of phase contrast, and I don't like this. Okay, we did that for PVDF, for example. Very thin, very low piezoelectric, very low signal. So when you have no choice, of course, you use it. But most of the time on oxide, we don't use it. Even on very, I'll show you later on, even on one nanometer of BTO, we didn't use it. Okay, this one, what I've just explained was for polarization out of plane. But of course, sometimes you have a component in plane. And wow. So the in-plane, oops. You see what the in-plane oscillation is going to produce? Torsion. Unfortunately, in a real modern AFM, there is no 2 photodiodes, but 4. So if you use this pair and this pair, you measure deflection. If you use this pair and this pair, you subtract the signal coming from these guys and these guys, you measure the torsion. At the same time, the signal remains the same on the photodiode. You can just make the difference of those, or both at the same time. And this is what we're going to use to measure the in-plane component of the polarization. Okay. Your cantilever is going to be distorted this way. Of course, if the stiffness is too high, instead of following the oscillation of the substrate, your probe is going to slide on the surface. So you get a reduced signal. So on the contrary of the out-of-plane PFM, here you have to prefer soft cantilever. If you want both, take a 10 Newton per meter cantilever. You're going to have some artifact, but sometimes you don't care. You just want to have a raw information. Okay, so if the polarization is in this direction, you have the maximum signal. In this direction, this top view. Huh? 0 signal, and of course, if you are in this direction, what you are going to measure is the projection of the polarization on the axe orthogonal to the cantilever. Of course, if you rotate so you have one component here, you rotate your sample by 90 degrees, you will have the other component, and then you can have full determination of the in-plane polarization vector, but thanks to the out-of-plane PFM, you have also the component of the out-of-plane, and then you can reconstruct all the vector of your polarization. This is called vectorial PFM. Okay, let's make an exercise on what? On BFO. So there is 8 possibilities in the 1-1-1 direction. Okay, let's call them P1, P2, P4, P4, plus or minus depending on up or down. Okay, I bring you a sample of BFO on SRO and DISCO, and this is the topography. Then, this is the out-of-plane measurements. No, this is the phase image. No contrast. Only one component out of plane, either up or down. In this case, it's down. So I have 4 possibilities. P1 minus, P3 minus, P4 minus, P2 minus. Of course, I know my sample, so I put the cantilever parallel to the 110 direction to be sure to be parallel to the polarization, one of them. So, and this is the amplitude. So when it's white, there is amplitude. Where it's black, no amplitude. So where it's white, you have P minus 1 or P minus 3. Where it's black, you have the 2 other possibilities. If I look at the in-plane phase now, it's the same measurement. Huh? I can make the difference because here, if it's P1, it's black. If it's P3, it's white. And if it's one of the others, it's black too. But I don't care. I know where my interesting projections are. Then I can rotate the sample by 90 degrees. I do exactly the same thing. And then I know exactly, I have full pictures of my domains. And so the domain walls too. Yeah? I hope so. Here? Because of the phase.
Yeah, but could it also be the other way around? Like P1 is white?
Yes, of course. No, yes, of course. You have to know your FM to know who is black and who is white. I mean, it comes from a lock-in. So I can just turn the button of the phase, and then black become white and white become black. So what is interesting is just the comparison. No? See what I mean? Okay. I told you that it's possible to write artificial domain out of plane. It's easy to understand. It's here, you reversed it. But you can do also in plane. This effect is called trailing field. And in fact, depending on, okay, here you have in-plane phase, so you know that there is a domain this way. And if you scan, so it's in-plane component, and you see if I scan with a DC, high enough DC voltage, if I scan in this direction, or if I scan in this direction, I can select one or the other polarization. So I can write domains out of plane, but also I can control, potentially, the in-plane component of the polarization. So that means that you can create various domain walls, even though that are naturally not favorable. Okay, we'll see that a little bit after. So here also I would like you to understand that it is possible to make PFM imaging through an electrode. Of course, if you apply an AC voltage here, this is let's say a gold pad, and this is a ferroelectric material. If you apply an AC voltage on the probe, this voltage is going to be exactly the same on all the pads, and everybody is going to oscillate depending on the orientation of the polarization. But because this is your probe that is probing locally the oscillation, the probe does not care that this oscillate for a down domain. This probe is going to feel, of course it depends on thickness, is going to feel what oscillate just below it. So it means possible, and this is a proof. So this is a pad deposited on a tunneling, not tunneling barrier, in this case it's a thick BFO. You can see here the mixed state has grown, at least after lithography. And if you apply a voltage, you can reverse down or up. And by using pulses, you can even come back. Instead of applying DC voltage to make it up or to make it down, you can use pulses to reverse just partially, and you can come back to. But you cannot make a drawing, of course. Huh? Okay, and with this kind of measurement, for example, you can study the switching dynamics of the PZT capacitors. Okay, so at this stage, we're able to make vectorial PFM. We can determine all the components of the polarization vector. With a DC bias, you can write out-of-plane polarization variant. And with a trailing field, with this DC bias, you can even select the in-plane component of the polarization. So all polarization configurations can be determined and potentially written. And at this stage, I remember you that you are the king of CTF, of scanning resistance AFM, and the king of PFM. So let's try to combine them to study the conduction of domain walls. So this is neutral domain walls, which is more favorable, of course. And this is a charged domain wall that you were able to draw thanks to the trailing field. And now, if you use the scanning resistance microscope, you can see that there is at least 2 or 3 orders of magnitude in the conduction of the neutral domain wall compared to the charged domain wall. So, if you're interested in conduction in domain wall, scanning resistance microscopy is for you. And PFM. Okay, there is a even much clever way to... Putain, 1h10 déjà? Ferroelectric tunnel... Yeah, the boss sent us an email saying it's 1 hour. Okay, it's already 1:10. Sorry, Dad. Okay, ferroelectric tunnel barrier. This effect was predicted in the 70s by Leo Ezaki, very famous guy, and he said maybe if we can make a tunneling barrier thin enough, ferroelectric, we can have a different resistance state. So I go faster. No, it's too... Okay. Sorry, guys. But this is the answer. Yes, BTO can be ferroelectric at very small thicknesses, as you can see here. And yes, thanks to the scanning resistance IFM, so there is a huge difference in the tunneling transmission of up or down polarization orientation. This was the first demonstration of ferroelectricity-related tunneling electroresistance just by scanning probes. So it can be fun too, huh? So I switch that. You can do exactly the same thing. Okay. So scanning NV magnetometry. So I have few slides about it, but I wanted to talk about this because it is something very new in the field. The first proposal was made in 2005, first paper in 2008, but those kind of systems and probes are commercially available only since 2020. You need one, for sure. Okay, what is the NV defect? This is it. This is diamond. And usually you produce it by irradiation with nitrogen. So here you have a vacancy. Here you have a nitrogen atom instead of carbon, antisite. So this defect produces levels within the band gap. And so this defect is optically active in the visible. So if you use a green laser to excite it, then you recover a red photoluminescence. Okay, that's why there is called to diamond. So the properties of these things has been deeply studied for maybe 20 years because it can be used as a qubit in a quantum processing science. But for us, it's enough to consider that these things is a embedded artificial atom is a diamond lattice, except that it has a very specific quantization axis, which is the axis between N and V. So there is only one electron. This system is a one electron system with a spin triplet as ground state. So, and what you need to know here is that the state 0 is bright relatively to its photoluminescence, and the state plus or non-zero spin is dark. I mean, if the electron starts here, get the photons, green photons, at the end there is 25% less, 25% less photoluminescence compared to if the electron comes from here. So you have a spin-dependent photoluminescence signal. Now, if you use a microwave antenna to excite this system, this is what you get. This is the photoluminescence versus the microwave frequency. And as soon as the frequency reaches the difference of energy between those levels, you have the electrons, the so-called electron spin resonance, and the photoluminescence drop by 25%. Now, if you apply a magnetic field, then you split plus and minus 1. Of course, the splitting is related to the projection along the quantization axis. And then puff, microwave, too deep. Two dips. And the distance between those dips is directly related to the magnetic field. And as you can see, G, mu B, there is nothing else than constant. So the NV, where it is, it's an absolute magnetometer. Okay, so fast, we need what we need. We need an IFM. We need an IFM probe with a single NV at the end. We need an objective and a microwave antenna. This is how it looks in real world. Okay, and okay, this measurement is quantitative, is vectorial, with a very good sensitivity. I would say something like 2 or 3 orders of magnitude better than MFM, magnetic force microscopy. There is no back action, unlike in MFM. The atomic size detection volume is small. Well, atomic size detection volume is so small, but the spatial resolution depends on the distance of the NV to the sample surface. Okay, so, but you need an NV-based sensor. So let's start with the dark edge that explains why this system was not widely used before 2020. So, to fabricate such a probe, you take a bunch of diamond nanocrystal, you hydrate them with nitrogen, you throw them on the table, and with optical techniques, you are able to know which one contains 1, 0, 2, 3 NV center. Once this is done, because those guys tend to be negatively charged, you cover your tip with a cationic polymer, positively charged, and you try to fish the proper diamond nanocrystal to put it on your probe. Then with a PL map, you can check it is here. And, okay, you can imagine that this technique is extremely time and student consuming. Huh? And because nature often is a bitch, you cannot stick this guy at a distance smaller than 100 nanometers. So the resolution is pretty small. You have a random orientation on the NV axis, and the worst, regular IFM probe are quite fragile. I don't care to change an IFM probe twice, 3, 10 times a day, except if the student spent 2 weeks to fabricate this guy. And the solution came from Switzerland, the Swiss edge of all diamond probe hosting a single NV defect. Those are commercially available since 2018 from 2 Swiss companies. This company paid to be a sponsor, so appear first. Qnami is the other one. So Qzebra is cool. Qnami is cool too. Huh? Not that much. And this is how it looks like. This is full monocrystalline high purity diamond. This guy was etched out from the thicker pure diamond plate at the end. And what is important is that the NV is just there, within a slice of 50 nanometers.
But this is not a 15 euros.
You kill my joke. You just killed my joke. Yes, you do. This is the only way you can hear me saying, don't change the tip, try to save it because it costs 3,000 euros. Switzerland. Diamond from Switzerland, okay? So this is a photoluminescence map of the diamond probe from top view, and you can see here there are a lot of defects coming from the process technologies, but here you have your single NV. The distance is below, okay, it's about 50 nanometers, and you can control easily the NV axis orientation because it is monocrystalline. Okay, so blah blah, you can do a lot of things. Finish. Okay, it's not that important, but I wanted just to show you what can be done. Oh, BFO again. But in this case, we know why, because we want to make PFM to study the ferroelectricity. We want to use a scanning NV magnetometer to study antiferromagnetism, and this guy is the only one that possesses both properties at room temperature. Okay, so please. So 8 possibilities of polarization. And for the antiferromagnetic order, you have a spin spiral, a spin cycloid, along 3 possible propagation axes in the plane perpendicular to the polarization you have. Okay. So this is a nice paper from our lab showing that what's going on with the strain. So you take this B layer and you change the substrate and you obtain different strains. So in all cases, it's a single domain out of plane, P down. And in all cases, This is a ferroelectric stripy domain with only two configurations in plane. Either this one, either this one. All in the same direction, pointing down. And now, if you use your nice scanning NV magnetometer, this is what you see. In each ferroelectric domains, you have antiferromagnetic domains. Except it's here. It came back to the G-type antiferromagnet. Okay, cool. But if there is a single relationship between ferroelectric, antiferromagnetic, and if I can control the ferroelectricity, maybe I could control the antiferromagnetic state. We won't know. So you take your best PFM probe and then you write a domain. And you go to the scanning NV magnetometer and you found that there is a nice cycloid in this direction. And if you do the same thing but with another polarization orientation, you are able to change the antiferromagnetic orders. It's fun. It's so fun that you could imagine to do crazy things like that, but it's another story, and it was a poster of Arthur, but too late. It was the first station. Next time we have to synchronize a little bit. Okay, so I finish in 1 minute. Okay, it's absolutely not related to oxide in this case, but I love it. Okay, when I was a student, I always heard it's impossible to have atomic resolution with AFM. Only STM can do that. It's not true. You can have easily, 1,000 students around the world get atomic resolution every day with an AFM. But here, what is most impressive is that you can see the position of the atoms, but you can also measure some chemical bonds with an AFM. It's so cool. If you want to know how it's possible, I advise you this nice paper from the Pope of non-contact AFM. It's very well explained, no equation, just basic concepts, wonderful. And I want to finish with that. This is the last slide. This is, this is life science. It is known that the myosin 5, I don't know, hope these guys know that without AFM. It is known that this molecule is used as a motor protein that will transport things inside the cell, running around actin filaments. Don't ask me what are these, but what I know is that. It's a real time. Look at this. No, it's great. No? It's a molecule running around in a... Great. Okay, so just to tell you what's possible to do with an AFM, you can have a molecular resolution and you can have almost a real-time imaging of what's going on there. Thank you for your attention. Thank you, Steve.